Before we begin, a quick note. All the tactical data, hardware specifications, and timelines discussed in this video are sourced directly from publicly available defense white papers and unclassified research reports. On May 7, 2025, the Indian Air Force launched a highly coordinated strike package targeting 9 heavily fortified logistical hubs deep inside hostile territory. Navigating a gauntlet of advanced Chinese-supplied HQ-9P surface-to-air missile radars, the Indian jets neutralized their targets and egressed the airspace in exactly 23 minutes. This mission succeeded by mathematically hijacking the physics of the radar systems tracking the strike package. If you want to reverse engineer the specific waveforms used to blind these sensors, hit the like button and subscribe. During the 1971 war, the Indian military operated in a pre-electronic warfare environment. If commanders needed to blind a hostile radar station, their only option was to fly legacy hardware like the Canberra bomber directly over the installation and drop high explosive ordnance onto the antennas. Modern survivability relies on full spectrum dominance, maintaining control over the invisible electromagnetic spectrum through targeted radio waves. In an era of networked, frequency-agile sensors, attempting a purely kinetic bombing run against an integrated air defense system is highly suicidal. Operations Indoor relied on this non-kinetic spectrum denial. By exploiting the processing logic of the adversary sensors, the Indian Air Force rendered multi-million-dollar air defense networks blind, allowing the strike package to operate untouched. To understand how they did this, look at this diagram illustrating the radar range equation. A ground radar operates by blasting a high-power radio wave outward. As that energy travels, it disperses into a massive sphere, losing power. By the time it hits a distant jet, only a microscopic fraction of that energy bounces back as an echo. The physics dictate that this returning signal decays proportionally to the inverse fourth power of the distance. Now, look at the mathematical advantage of an active jammer mounted on the aircraft. The jet broadcasts its own radio energy directly at the ground receiver. Because this artificial signal only travels in one direction, its power decays much slower, specifically to the inverse square of the distance. At long range, this massive one-way wave easily washes out the tiny natural radar echo bouncing off the jet's hull. But physics dictates a closing window of vulnerability. As the aircraft physically approaches the radar dish, the strength of the natural echo increases exponentially faster than the jamming noise. Eventually, the jet crosses the burn-through range. This is a highly specific distance where the natural echo finally pierces the jamming interference, revealing the aircraft's exact location to the enemy operator. Historically, pilots frantically tried to beat this burn-through range by simply blasting louder, brute force static to raise the noise floor. Modern software-driven radars use rapid frequency hopping and complex pulse compression to filter out that background noise, rendering traditional jamming obsolete. To defeat these advanced sensors during operations indoor, the Indian Air Force utilized digital radio frequency memory, or DRFM. A DRFM suite actively intercepts the incoming enemy radar pulse, digitizes it using ultra-high-speed converters, and stores a perfect mathematical replica of the adversary's exact waveform within a few nanoseconds. Because the copied signal is perfectly coherent, the jammer uses it to execute a range-gate pull-off. The aircraft fires the exact same radar pulse back at the ground station, but introduces a tiny, calculated timing delay. On the radar operator's screen, the automated tracking box locks onto this duplicated ghost pulse, dragging the targeting crosshairs miles backward into empty space. By projecting dozens of these moving false targets, the Indian Air Force mathematically erased their strike package from the adversary's HQ-9P tracking screens, securing their 23-minute window of invulnerability. Unable to utilize their blinded air defense radars, the adversary immediately pivoted tactics. Over the next 3 days, they launched an asymmetric retaliation, sending a barrage of over 600 drones, rockets, and cruise missiles, targeting vital Indian military installations. Successfully intercepting hundreds of incoming targets simultaneously relies on a fully fused multi-domain network capable of sorting threats in real time. Isolated missile batteries cannot manage a mass saturation swarm of this magnitude. India managed this defense through the Integrated Air Command and Control System, operating in tandem with the Army's Akash tier network. This digital backbone synthesized data from terrestrial radars, civilian reports, and 360-degree look-down surveillance from airborne early warning aircraft like the Netra into a single real-time picture of the battle space. Armed with this unified data, the high-altitude kinetic defense grid activated. S-400 batteries and indigenous Akash missile systems seamlessly intercepted the high-speed cruise missiles. The network's integration ensured perfect handoffs, preventing multiple batteries from wasting interceptors on the same target. But the high-altitude missiles couldn't solve the gray zone threat. Cheap commercial quadcopters flying so low they slip beneath the horizon of traditional radar. To defend the lower-tier airspace, localized counter-UAS grids utilized micro-Doppler radar to detect the minute frequency shifts generated by spinning drone rudders. Once a micro-drone is verified, the system executes a sequential two-stage kill chain. First, it deploys targeted jamming to sever the command link. If the drone flies autonomously and ignores the jamming, the system escalates immediately, utilizing a high-power laser-directed energy weapon to physically burn the drone's structural components out of the sky. This multi-layered interception proved that the domestic airspace is protected by an interconnected, self-healing electronic shield, capable of identifying and neutralizing everything from a supersonic missile to a modified commercial quadcopter. When the skies cleared after 88 hours of continuous conflict, the operational data confirmed the outcome. Despite the launch of over 600 drones and missiles across 13 distinct frontline locations, 0 Indian military assets were lost. The physical recovery of downed Turkish-designed drones and Chinese-origin PL-15 missile debris from the conflict zones provided tangible proof of concept. The indigenous electronic warfare architecture successfully unraveled the processing logic of advanced foreign-supplied hardware. However, the window of effectiveness for current DRFM technology is already closing. Adversaries are actively developing ultra-wideband radars that feature entirely unpredictable, constantly shifting pulse repetition intervals. Relying on static threat libraries to counter these agile sensors will soon result in a failure to intercept. The next requirement in spectrum dominance is cognitive electronic warfare. This involves injecting artificial intelligence and machine learning directly into the hardware's rapid processing loop. Instead of simply looking up a known threat in a pre-existing database, these AI systems are designed to autonomously analyze entirely unfamiliar, zero-day radar emissions as they occur. Within milliseconds, the neural network evaluates the unique waveform, synthesizes a bespoke jamming algorithm, and dynamically adapts to the enemy's countermeasures in real time. Mastering the cognitive spectrum is the technical requirement for maintaining operational superiority in future multi-domain conflicts. If you want a deeper dive into the exact machine learning algorithms powering these cognitive systems, let me know in the comments. Hit subscribe and tell us what defensive architecture we should reverse engineer next.